exam. So if we think about all the shapes that are around us in actual load-bearing structures, maybe the cross-sections of those beams that we spoke of earlier, something like an I-beam, we know that very oftentimes the actual areas can be decomposed into a concatenation of very simplistic shapes. If you've ever taken a CAD course, the idea of doing modeling often relies on this. You have these basic primitive shapes and you put them together and you take combinations of them and you make more complex shapes. So in terms of actually computing the moment of inertia, doesn't it feel like we could have a table somewhere where somebody already did all the work of that integration that we did in the last problem for us? And that is true. But what really is going to make these type of problems hard is if we were to try to tabulate the moment of inertia of shapes. Remember that entire approach that we did in the last problem required actually defining an axis about which we computed the moment of inertia. Now, you might say, well, we'll always use the x and y axis. But what if the area sometimes is right on the x-axis? And what if sometimes it's moved up and sometimes it's shifted and whatnot from there? There's very often times we're going to need to define the moment of inertia about a ton of different axes. But the hope is that they'll all always be parallel to either a purely vertical axis or a purely horizontal axis. So if we only had the ability to put in the table the moment of inertia of common shapes about a vertical and a horizontal axis that went through some common point on that shape, and we had a way, given that knowledge, to determine the moment of inertia about an axis that's parallel to the purely horizontal or vertical axis, then we could reduce all that integration work that we did in the last problem to a simple table lookup. And that's exactly what the parallel axis theorem will allow us to do. Basically, we're going to use tables to look up the moment of inertia about axes that run vertically and horizontally through the centroid of a shape. And then if we're ever asked to, if that shape happens to be shifted, and we're asked to find the moment of inertia about a horizontal or vertical axis, we'll use this relationship here, which is really the parallel axis theorem. So it looks really confusing, but here's what it's basically saying. If I want the moment of inertia about some horizontal axis, if I can look up the moment of inertia about a horizontal axis that runs through the centroid, and I know both the area of the area that I'm computing the moment of inertia of, along with the separation distance of the new axis from the centroid. So that's what this dy squared is. And I don't really like that your book uses dy. Kind of delta y is a little bit better approach to me because it's not an infinitesimal distance. It's actually a physical distance. So putting an actual label on it here, if you notice we have this blue area shape, and we're told that its centroid is this point C. We know assume that someone has already done the work for us for knowing the moment of inertia about this axis x prime and y prime. X prime is horizontal and it runs through the centroid. Y prime is vertical and it runs through the centroid. If we want to compute, say, for example, the moment of the inertia about this horizontal axis, x, since we know the moment of inertia about x prime, we can just use this formula. We take the moment of inertia about x prime, we take the area of this shape, and we multiply that offset distance between x prime and the axis that we're interested in. So it looks a little bit confusing when you first see it written in formulas, but the general idea is you're trying to reduce this to something that you can do kind of through a tabular and table lookup approach. Another important term to know is this idea of the radius of gyration of an area. It's not covered much in the actual statics course, but when you move on to strength of materials, it's something that you're going to see again. And just know that it's a measure that involves the moment of inertia. And it's used, the mention that's, it's used in many different places in this, but your book particularly brings up the fact that it's used in the design of columns in structural mechanics. But it's related to the actual moment of inertia. Namely, I can define a radius of gyration about the x-axis by taking the ratio of the moment of inertia in x. Remember that's in units of length to the fourth, divided by the area of that particular body, which is going to be in units of length squared. So length to the fourth divided by length squared is going to be length squared. When you take the square root, this will just be in units of length. So it's just a measure of related to the moment of inertia about both the x-axis and the y-axis. So the only thing that really matters in your statics course is sometimes they ask you to compute that, and it's something that can be computed. The reason I showed this formula is if you know ix and you know a, it's a quantity that you can compute, and it's a quantity that takes on the same units as just simple length. So in terms of how you actually set this up, if you have a composite area, and by a composite area, I mean something that you can break up into kind of a concatenation of a bunch of simple shapes, like maybe you have a square with a triangle on top. That area might look a little bit funny. And in your table, there might not be a lookup for the moment of inertia with a square with a triangle on top. However, there will be one for a square and there will be one with a triangle. So you're breaking it up into those fundamental parts. That's what step one means here. Next, we're going to look up in the table what the moment of inertia is for a horizontal and vertical axis through the centroid of each of those simplistic parts. And then we're typically going to be asked to find the moment of inertia about another axis. We're going to measure that distance away in the vertical and horizontal directions, and then we're going to apply those principles of the parallel axis theorem that we looked at previously. The only thing you want to be careful of is in the textbook, oftentimes they will give you composite areas that are formed not by combining two shapes or summing them together, but by taking a set difference or actually subtracting. And in that case, when you apply the parallel axis theorem, you just treat the area like a negative number, which will actually reduce the moment of inertia because you're going to have less area away from that axis. So let's see how we go about solving this problem. Here we have some sort of composite shape. It looks like you can kind of make it by subtracting a circle away from a rectangle and a triangle. So we're going to break this into rectangle, triangle, and there's actually, as I'm saying this, I see that the book actually did this a little bit different. They take a big rectangle, which they're calling A here, which is going to be 300 millimeters high and actually 350 millimeters wide. And imagine that was all there, and all you did was subtract away the triangle and subtract away the circle. But you could do it the way that I was describing earlier, to break it into this rectangle, this triangle, and just subtract away the circle. There's really no difference in which approach is easier. In both cases, you would have to look up the moment of inertia as a three different shape. And sometimes that's what actually takes the time. So again, A just corresponds to this entire rectangle that includes this portion that's chunked out. B is just a circle, and C is this triangle. And then what you're going to do is look up the moment of inertia of each of those shapes, and we'll see what those are in a minute. But in each case, we also need to know what the centroid of each shape is, because we need to know the perpendicular distances from our axes of interest. So here we're trying to find the moment of inertia about the x-axis. So say, for example, a circle, right? There's two lines of symmetry there. So its centroid is going to be right in the middle. Notice that if I draw a horizontal line through the centroid of the circle, that it's 150 millimeters above the actual x-axis. So that's how they're getting this dA equals 150 millimeters. What they're saying is that I should say in that case dB. That turns out dA is the same. But since the centroid of the circle is right in the middle here, it's a horizontal line that goes through the centroid is 150 millimeters above the actual x-axis. The centroid of the rectangle, it also has two lines of symmetry. So what we will find is that its centroid is also elevated by 150 millimeters. That's why these two things are the same. Remember, for a triangle, the way that you actually find its centroid is you go to the higher end. Notice that it tapers towards the higher end here, and it's 1/3 of the way down. So if you divide this 300 into 1/3, the centroid would actually be 100 millimeters down. So the actual distance to the x-axis, there we go, would be 200 millimeters. So that's where they're getting these three numbers. They're just the distance from a horizontal line drawn through the centroids of each of those shapes to the actual x-axis. Now we actually have to look up what the moment of inertia for each of these shapes is, and I kind of took this from the back of your text. Back of your text really becomes a hard thing to do when you have an ebook and you don't have the actual text that you can just flip to the back. So I tried to tabulate them for the ones that you need for you here. So the actual circular area, if we define the moment of inertia about the x-axis, if you were to do the integration, you would see that it's 1/4 pi r to the 4th. And why are the moment of inertia about the x and the y the same? That's because this is purely 360 degrees symmetrical. So we wouldn't expect them to be different. Here, the moment of inertia for this rectangle drawn with the width in x and the height in y, you notice that in x, it is going to be 1/12 bh cubed. And in y, it is going to be 1/12 hb cubed. So it's kind of like the b and h are just swapped when you go to x and y as expected. And then for the triangular area, here we're measuring the moment of inertia from the base, and we notice that from this base dimension, it's just going to be 1/36 b times h cubed. So if you have another base there, you just would adjust your formulas appropriately if you're measuring it from another axis in that case. So in terms of computing what these moment of inertias are, here, everything that they have to the right is parallel axis theorem stuff. So remember that according to the parallel axis theorem, you multiply the area times that perpendicular distance squared. And here are the perpendicular distances, like 150, 150, and 200. So that's why they have the 150 squared, the 150 squared, and the 200 squared. These are just area computations. So remember that shape A is the actual rectangle. The rectangle has a height of 300 millimeters, a width 350 millimeters. That's why 350 times 300 gives you your area times this perpendicular distance squared. Of course, this 1/12 base, I should say, where are we at? The 1/12, that is the width times the height. It's nothing more than the moment of inertia here. So a little bit hard where I'm flipping back and forth between slides, but try to actually draw these out in front of you and match them up to the formula. And you will see that this first term is basically a table lookup in each of the three cases. And these are parallel axis theorem adjustments. Now, why in the actual final summation are they taking A and they subtracting away B and C? Well, that's because the shapes corresponding to B and C are both holes. And since they are holes, you will subtract those by definition. It's kind of like you're treating the areas as negative. So given the total aggregate area of moment of inertia about the x-axis, how can we find the radius of gyration about the x-axis? This is kind of what I was saying a little bit earlier. It's just a bit of a table lookup. If you know Ix, we can compute the aggregate area here by finding the total area of the rectangle and then subtracting away the area of the circle and the area of the triangle. And once you have those two numbers, it's really just a matter of being able to take a square root. So hopefully